Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to the organ printing course. So in the last lecture we have discussed on bioprinting, that is extrusion based bioprinting technologies, that is the principle, working status, current status and all these different things. So today we will see the rest of the things in extrusion based bioprinting. So we'll start with this extrusion based bioprinting strategies. So we know how actually extrusion bioprinting works. This technology works on the extrusion principle, that is extruding materials through a nozzle, putting the material inside a syringe, then pushing the material either by pneumatic or mechanical pressure, and then extruding the material in the form of filament, and then plotting them on a print stage or print bed as per the design into a 3D structure in a layer by layer concept. So depending upon the way, the strategy here can be different types. Like the very first one is when we print only with cell-laden hydrogel. Hydrogel you know very well, where we use hydrogel as a vehicle for cells to deliver or encapsulate cells within hydrogel. Hydrogel provide all the necessary conditions for the survival, proliferation and also supports migration of this encapsulated cells. So the cells are in viable condition when we encapsulate them in hydrogel, and we provide all necessary conditions like nutrition, oxygen, all these things, whatever is required for survival of these cells, we provide them when we encapsulate them within the hydrogel. Now this cell-laden hydrogel, but most important thing, when we use this hydrogel for encapsulating cells, the viscosity, we should take care of the viscosity of the hydrogel. Like we can use low to moderate viscous hydrogel. Very high viscous hydrogels are not generally used because that can hamper the cell viability, cell proliferation. So mostly we use low to moderate viscous hydrogel. Now this hydrogel, when you are to try to print a structure with extrusion based bioprinting extrusion based bioprinter, then because of this low to moderate viscous of this hydrogel, we cannot print a very good structure. Mostly the structure we design and actual printed structure, there is a difference between these two. So the structural fidelity or the printing fidelity, that means after printing, the outcome of the structure, how close that is to your design 3D geometry, it is different than others. So that's why this cell-laden hydrogel, they are very difficult to print into a three-dimensional form. Because mostly what will happen, whenever we print this hydrogel on the stage, there is a deformation of the shape. So it doesn't conform its shape like when it comes out as the form of filament, but when you put them on the print bed, then they deform. Now when you put the next layer, then again this layer, because of this gravity, they just collapse. Right? So we cannot make a very high the structure that is of high, the height is more. So we end up printing, suppose like 4 layers or 10 layers, but mostly the height, we cannot achieve a great height with this only cell-laden hydrogel because of this inherent inherent properties of this hydrogel, where they just collapse. We cannot put them one layer up one another. So that's why some kind of structure, three-dimensional structure, is required for this hydrogel, so that then they can be able to retain the shape and size of the printed dimension. Now there are different types of hydrogels are used for bioprinting, starting from alginate, collagen, gelatin, fibrin, silk, where different types of material can be used. What are the different types of hydrogels mostly used for? Other applications like tissue engineering, and all of them have been tried to print 3D structures using extrusion-based bioprinting. But the most important thing is to remember is that whatever the hydrogel we are using, the viscosity should not be very high. But the most challenging part is to print them into a required size and shape where they can retain the shape. The shape retention is not that great with Cellulated hydrogels. So we'll see what are the different ways we can overcome this. So one such way is to using some sacrificial materials, but this is also true for when our intention is to print a complex geometry, something like suppose our intention is to print a printed ear shape structure. Then you see the ear is a very complex shape, so not all the things are on the same plane. They are having we have some ups and downs in the geometry, so there are different planes. So, and in 3D printing or in bioprinting, we cannot print anything on ear. We have to provide support to all the structures we are printing. So that's why when we are printing on stage, we directly plot the material on the stage directly and then print in a layer by layer manner. Now suppose if you have a geometry that is something like this geometry, then you have to provide support to this whole hanging geometry. This is the hanging geometry when you print them on the plate. So these all things we have to provide support. Now this support material are mostly named as sacrificial materials in bioprinting, because these are of sacrificial nature. After the printing is done, we are going to sacrifice those material. Those are mostly not used for this bioprinting, for making the structures. So that's why this and there are various sacrificial materials are being used for extrusion-based bioprinting. But one important thing to remember here is all these sacrificial materials should be solubilized or should be soluble in water. Why? Because when you remove the material after bioprinting, because there are cells also there inside the hydrogel, we cannot remove the sacrificial material just by washing with any organic solvent. We cannot use any organic solvents, any other solvents. Only we have to use water soluble materials as in sacrificial material, so that can be removed without causing any harm or toxicity issue to the bioprinted structure. So that's why, but sacrificial materials are very important when you are trying to make a three-dimensional structures of complex geometry having a lot of overhanging sides, overhanging space layers. So there we need to provide a support structure needs to be made with sacrificial material. Another type is where, because with Cellulated hydrogel we cannot make the printing fidelity is not very good, so we cannot make very good structures. The height we cannot maintain very good height. So that's why what we can do, we can also combine with thermoplastic polymers. That means we are not combining the hydrogel with thermoplastic polymer, but we are printing simultaneously thermoplastic polymer and hydrogel both. First, with the thermoplastic materials, the framework can be made, and then in that framework, in every layer, the hydrogels can be simultaneously printed in between the framework. Right? So this process is called combination with thermoplastic polymers. This is also called hybrid bioprinting, where both thermoplastic polymers and Cellulated hydrogels are being used. But one important thing to remember is, thermoplastic polymers are mostly used for fused deposition modeling or fused filament fabrication based 3D printing techniques, where the process is very similar to extrusion based processes based on extrusion based principle. But here what we do, we melt the thermoplastic polymers. Those are mostly used in the form of filament. So those filament, when it pushes through the print head, because it has micro heaters, it heats up and then heats up the material. So thermoplastic polymer that liquefy, now then again when you push them, they comes out in the nozzle as a molten thermoplastic polymer. So that molten material or that liquefied material can be plotted on the stage. So thermoplastic polymers, that works on a similar concept like our extrusion based bioprinting, but here thermoplastic materials are used to make the structures. Now here, in case of combination with thermoplastic polymers, that's what we do. We print the framework with thermoplastic polymers, and later on, in between the framework, we print the cell-laden hydrogels, and these cell-laden hydrogels are being plotted so that the thermoplastic polymers that make up that hold up the whole structure and doesn't allow the hydrogel material to deform, but basically it holds the material so we can get the height. So that's why this hybrid printing is a very important idea where we can achieve height as well as very good printing fidelity. But one concern is these thermoplastic polymers are very typically, they are of the mechanical properties on the higher side. So how they can interact with the soft tissue, that is one challenge that we have to always address. Another important thing to remember is whatever the thermoplastic polymers we are using, because of this, that the printing process is such where we liquefy the material by applying heat and then extruding. So the liquefaction temperature of this thermoplastic polymer is a very important thing to note down here, because we cannot use any thermoplastic polymer where the liquefaction temperature is very high. So that's why mostly PCL or polycaprolactam having liquefaction temperature of starting from 60 to 90 degree or 100 degree. So that's why it can be very well used for as a material for hybrid bioprinting, because if the liquefaction temperature is not very high, during the process of depositing that material, the liquefied material, that dissipates heat, and when it reaches to the stage, generally it cools down. So that's why it doesn't cause any heat induced damage to the cells that is encapsulated within the hydrogel. So that's why this technology can work well. Now let us see how actually both this process works. First, with the cell-laden hydrogel, in this video you can clearly see that here we have a material that is gelatin where we have encapsulated the cells, right? And then now we are printing a lattice kind of structure. So lattice structure is when it is printing, the first layer is printing, suppose this is 0 degree, then the next layer will be printed at 90 degree to the preceding layer. Now here, if you can see, they are the process parameters. As I mentioned earlier, the process parameters are very important. Here we have mentioned the process, like we have used a 200 micrometer nozzle, and the printing temperature is around 28 degrees centigrade. We have applied pneumatic base extrusion pressure. So where the pneumatic pressure is almost 0.2 bar pressure we have applied, and the next thing is the print speed, whatever that is 20 millimeter per second. So that's what we have used here, a lattice structure that is shown here, printing a lattice structure with cell-laden hydrogel. But this, as I already mentioned, here the structural fidelity, the printing fidelity cannot be very good because of this nature of the hydrogel, that when you print them, they don't retain the shape of this printed filaments, but they generally deform due to the gravity. So that's what happens. But anyway, but this is very important because the cells can survive this printing process. When we optimize all the printing parameters, then the cells can survive and they can very well be in alive condition after printing within the printed structure. So the if we can optimize all the printing parameters nicely, then the cells can survive this process, and cell viability can be more than 80% cells or more than 90% cells can be alive. The next printing process technology, that is the hybrid printing, as I have mentioned in the earlier slide, that in the hybrid printing, when basically we print both thermoplastic polymers, the framework is made with the thermoplastic polymers, and then later the cell-laden hydrogen can be printed within this. So in this case, we have seen this video In this video, it can be clearly seen this first the PCL framework is being printed. You see the first layer with the PCL framework. PCL is a thermoplastic polymer that is printed just by liquefaction and then pushing the material through the extrusion nozzle. So it is coming out. So we have created the first layer where then now this is the Cellulated Hydrogel where it is being printed in between the framework every layer. So here we have shown two different hydrogels can be used. So two different colors were being used to show just two different hydrogels can be printed at a time. And again, then in the next layer, again you see at 90-degree angle to the preceding layer, the thermoplastic material is being printed, and then again the hydrogel is again printed. So here in this video, we have clearly shown that with this hybrid bioprinting concept, we can print a very good structure with thermoplastic polymer and using cellulated hydrogels. But mostly also we can control or we can position the cellulated hydrogel at different location of this printed structures where we can control how we can basically print this hydrogel within the structure. So extrusion based hybrid bioprinting is a very important concept where we can take care of two things. One is the printing fidelity is very good here. Also we can position the hydrogel at different locations. Now again, the way we print the material on the stage using different things. So that can be, again, there can be different types. The very first is when we print only cellulated hydrogel, and you know very well that this cellulated hydrogel or only hydrogel is a shear thinning material. Shear thinning material means when we increase the shear rate, the viscosity of the material. Suppose if you plot shear rate and viscosity, shear rate on x-axis and viscosity on y-axis, then the viscosity with increasing shear rate, the viscosity of the material comes down, then it is a shear thinning material. Now shear thinning material are very popular for extrusion based bioprinting because of the reason that when we apply pressure on this, due to the applied pressure, there is the shear rate, and when it is coming out, the shear rate increases, and because of this increased shear rate, the viscosity comes down. So then the extrusion process becomes easier, so that we need less pressure to extrude the material in case for shear thinning material. So shear thinning materials are very popular, and because of this shear thin nature, less pressure is required so that there will be less damage to the cells. Otherwise, there is a concern in case of extrusion based bioprinting that when we apply pressure on this nozzle, on this syringe, and then when it comes out through the very fine nozzles, a shear stress can be generated on the inner wall of this extrusion nozzle. So due to the generated shear stress, that the cells can get damaged. So that's because of the shear induced damage. So that's why the cell viability can issue. But because of this shear thin nature, the requirement of pressure is less, and so that the cell viability can be well maintained. So when we use just only print bed, we are using not any other thing, and we are just plotting the shear thinning material on this print stage, then that process is only thing. Other important advantage of using shear thinning material is due to this nature, when the material comes out, it comes out in the form of filament, but as soon as it come out, because again then the shear rate is 0, then again the viscosity of the material increases. So due to that, the shape can be very well retained for shear thinning material. When you apply shear, apply pressure, the material viscosity goes down, it comes out of the nozzle, then again the viscosity goes up, and then the shape can be very well retained. So that shear thinning also helps in retaining of the shape of the printed structure. So that's an important advantage of this shear thinning material. Now the next is, as I mentioned in the last lecture also, that an important requirement for extrusion based bioprinting is the material should be in the form of fluidic. Material should be in fluidic nature when it is in the syringe, when it is actually during the printing process. But as soon as it comes out of the nozzle, it has to be solidified so that the shape can be very well retained. So this shape solidification can be done in various ways. We can introduce some kind of cross-linking. So that cross-linking, as I mentioned earlier, we can introduce either like photo cross-linking. That means if the material is of having photo cross-linkable, if we use a photo cross-linkable material, then by inducing light, we can induce cross-linking to the material so that the solidification process can start. Other than that, we can also induce chemical-based cross-linking. Like this, we can introduce some kind of chemical we can introduce that can cross-link this printed filament so that we can have this structure. We can have the structure can be very well treated. Also, we can also use ionic-based cross-linking. Like if we induce some ions to it, and if that ion interacts with the material and that it induces cross-linking, that can be another way to do that. So now here here shown is printing in a coagulation bath. Coagulation means when the material solidifies. Suppose the liquid or fluidic material, when it comes out of the nozzle and when it touches this bath medium, then it solidifies. So that because of that this process with this cause of coagulation bath. So here basically some cross-linking agent can be there in the bath as a cross-linking material. That can be either a chemical cross-linker or a ionic cross-linker. So anything can be possible. And then when the material comes out, it interacts, that material, extruded material interact with the cross-linking agent and then get cross-linked or solidified, and then that can be plotted here. Right? So this is another way where a printing in coagulation bath can be very well studied. Right? The next thing is when the printing in support bath. So in the later sometime in the next lecture, we'll discuss in detail what different kind of support bath is material. But one important thing to remember, a note here, is that because of this hydrogel, as I mentioned, printing only cellulated hydrogel is very challenging because the shape cannot be maintained. So printing a more or less two-dimensional structure is very well can be possible, but when we are using this, but when a complex geometry is required to be printed, then it is very difficult to do that with only cellulated hydrogel because there is no other support support given to the material during this printing process, and then that's it. But otherwise, let's suppose if we have a support bath material, the support bath basically it is holding the material during printing, then the printing becomes easier and we can make complex geometry can be very well printed. So printing in support bath is very important. Now support bath can be of different types. Either it can be a granular or microparticle based support bath, or it can be a colloidal or supramolecular assembly colloidal based support bath. We'll discuss this in detail later sometime in the other lecture. Now other printing strategy can be coaxial extrusion, because this is a syringe based approach. So now in the syringe we can have or basically I should say on the nozzle we can have two compartments, one inner core compartment and one other outer compartment. Now these two compartments, if the delivery of the material of these two compartments can be individually controlled, then what we can do, suppose when we fill the material and when it comes out of the nozzle, if it comes out through the inner core compartment and the cross-linking agent, suppose in this case whatever the cross-linking agent I have discussed, if those cross-linking agent can be supplied here through the side channels and then can come out and in the outer channel, then what will happen, then during printing itself we can take care of the cross-linking. What will happen, because the material hydrogel and the cross-linking agent both can be extruded or supplied, delivered at the same time. So what will happen, as soon as the material coming out, the cross-linking agent also comes out with it, and then it helps in cross-linking of the structure. This is one way to induce cross-linking during this printing process. So coaxial extrusion based printing very important here. This is what happens. So before extrusion the material is in the solid state, right? So this is basically it is a fluidic state, but when it comes out and it interacts with the cross-linking agent, it transforms into a gel-like state. Right? So that then when it becomes gel, then it can retain the shape of the structure. So that's why the structural printing fidelity can be very good when you are using this kind of cross-linking agent for our printing. So the only difference here is when we insert the nozzle inside a cross-linking bath and printing, because the whole needle is exposed to the cross-linking agent. Sometimes what happens, the clogging of the nozzle due to this over cross-linking, that can be a challenge, can be a limitation of this kind of when we print the structure inside cross-linking agent. But in this case, when we do that by coaxially extruding both hydrogel material and cross-linking agent, then we can overcome that challenge, and in that case the printing can also be very good. So here a detailed view of the same thing is given here. Like here, see this compartment, the inner compartment, this is the cross section of that nozzle, not crossing the longitudinal section of the nozzle, but this is the biowing that is coming. Suppose the biowing is coming through the inner core nozzle and the cross-linking is coming from to the outer compartment. Then what will happen, whenever the material is coming out through the nozzle, the cross-linkage touches the hydrogel material and it is getting solidified. So it is solved before extrusion, and after extrusion it becomes gel. Right? So this is the cross-sectional view of this thing. So bulk hydrogel fiber. This is one type of coaxial extrusion. Now in another case, we can also, what we can do, we can put the cross-linking agent in the inner core compartment, and the hydrogel material can come out through the outer compartment. In this case, what will happen, this cross-linking agent, as whenever it is extruding, like this case, this hydrogel and cross-linking together, then it will cross-linking from the inner core of the hydrogel. So from the inner part of the hydrogel, it will become cross-linking. So what we'll get, in this case we will get a bulk hydrogel fiber, but in this case we will get a hollow hydrogel fiber, because the cross-link agent present in the core of the hydrogel strand that prevents the material from coming together, preventing the bulk of the hydrogel and creating hollowness inside the hydrogel. So we can create a hollow hydrogel fiber. So depending upon the strategies, either we can create a bulk hydrogel fiber by instantaneous cross-linking with the cross-linking agent, or by judicially using cross-linking agent through the inner core of the coaxial syringe, coaxial nozzle, we can create a hollow hydrogel fiber. So these two are the possibilities, and there are many examples available in the literature where both these types are very well used for different applications. Right? So now we'll see what are the different applications of this extrusion-based printing due to various reasons, like user-friendly, ease of mechanism, ease of application, and also there is a less preparation time, like the hydrogel preparation of the biowing basically. So this extrusion-based bioprinting has been widely used across various laboratories for different applications. Another thing is this extrusion-based bioprinting, as I has mentioned in the earlier lecture also, it has got advantages of scalability, or a centimeter size tissue or the bulk tissue or organ can be very well printed with this technology. That's why this technology has got huge interest or huge prospect to develop various tissue engineered constructs. Like for tissue engineering, this technology has been used for different applications. Like people have been printing skin, bone, cartilage, trachea, liver, various other organs using different type of hydrogels. Because of this nature of this extrusion die printing, here with the layer by layer concept, we can print a three-dimensional structures, very well three-dimensional structures can be printed. We can control the mechanical property of the printed structure, and also, as I earlier said, that either we can use a sacrificial materials to print a complex shape, or also we can use the hybrid bioprinting concept where we print along with the thermoplastic polymer to print the structure. So those things are very much possible for, and then we can even, and when we use different types of structures, suppose for our interest is to print a skin, then skin is basically, if we consider it's a two-layer structure, grossly speaking, like suppose the dermis and the epidermis, then we can print the dermis and epidermis using two different extruder or two different nozzle. We can print one by one nozzle. We can even print the fibroblast cells encapsulating some hydrogel, skin tissue specific hydrogel, and then printed the dermis layer. And again, the epidermal tissue can be printed or can be seeded by seeding the like the keratinocytes, or keratinocytes can be also encapsulated within some hydrogel, and that can be printed on top of this. The skin tissue very well printed. Similarly, for bone tissue, people have been using hybrid bioprinting concept very well, where the thermoplastic polymers, because bone tissue is the mechanical property we need to maintain, or the mechanical property of the bone tissue is higher than the other soft tissues, so we need to maintain the mechanical property, where, so that's why hybrid bioprinting concept were very well used for bone tissue, where with the thermoplastic polymer we create the framework, then the bone cells like the osteoblast cells can be encapsulated in the hydrogel, and then that can be printed within this framework. Similarly, for cartilage tissue also, people have used this extrusion-based bioprinting, where the cartilage cells like the chondrocyte cells are encapsulated within the cartilage tissue specific hydrogel, either hyaluronic acid hydrogel or collagen hydrogel, and then that is being printed in the shape of cartilage, where the orientation organization of the cells can be very well controlled, and then we can actually develop a cartilage tissue. But here the mechanical properties cartilage tissue also is a kind of tough tissue, where the mechanical property we need to maintain. That kind of thing also research is going on. Another example is trachea, where people have been trying to develop a cylindrical trachea-like structure with the extrusion-based bioprinting strategy here. But one challenge is to generate this cylindrical structure, but there have been few examples in the literature where people have successfully developed the trachea-like structures with extrusion-based bioprinting. Similarly, though liver has very high regeneration potential, but has certain liver diseases or the liver, there is a need to generate artificial liver tissue. So with extrusion-based bioprinting, definitely, yeah, there are several attempts where with extrusion-based bioprinting strategy, people have tried to develop a liver structure using primary hepatocytes, or even in certain cases hepatocytes generated from iPSCs, and those hepatocytes are generally encapsulated in the liver matrix hydrogel, and then that is being printed, and that is used for generating liver tissue. Similarly, there are many other tissues people have been trying to print, like similarly kidney, pancreas, all the different tissues people have tried to print it with the thing. Another thing is the meniscus tissue is also being tried to develop with extrusion-based bioprinting strategies. Another major area of this extrusion-based bioprinting, cancer research. In cancer research, the main purpose of using extrusion-based bioprinting is the development of in vitro cancer model, where this cancer model can be developed by using cancer cells, encapsulating in hydrogel, and then printed them into a different structure mimicking the native cancer tissue microstructures and microstructure and the environment. And then if you can create that kind of microenvironment with bioprinting, then that tissue has a very high huge potential to be used for drug screening and also for fundamental studying the thing. Similarly, in the various in vitro healthy tissue or organ models have been printed with this extrusion-based bioprinting for drugs testing, where these models can be, if the model can mimic or recapitulate the native tissue architecture and function, or the structure and function, then that can be very well used for drug testing, because the way the drug will interact with this model, it will be very similar the way it should interact with the native tissue. So then we can use them at the very early stage of drug development, where we can see whether the drug has any toxicity to this models or not. And if the drug doesn't have any toxicity, then they will very well wait for further clinical study. Similarly, various tissue engineered organs are mostly used for transplantation. There is a huge demand of artificial tissues and organs, because we can say many patients who are actually waiting for transplants, and there are not enough supply or supply of these artificial tissues and organs. So those things can be very well studied. So transplantation of this thing, of the tissue engineered tissue or organ that is developed with extrusion based bioprinting, is another area, another application where this printing fits very well. Now let us discuss the limitations of this extrusion based bioprinting. Though this extrusion based bioprinting has various advantages, it has got some limitation due to the nature of this printing technology. Like, because it's a nozzle based approach, so always we are depending on the nozzle diameter. Because the nozzle diameter, the one challenge is we cannot use very fine nozzle, because what will happen, because we are using cells. So typically cells have dimensions like 10 to 30 micron size. If the cell, then we cannot use a nozzle that has diameter close to the cellular dimension. Then what will happen, when we apply pressure, the cells, we are pushing the cells through this very fine nozzle diameter, then there will be a lot of shear stress generated on this cell, and that can cause damage to the cell. So that's why mostly we use nozzles of some higher dimension, like 100 micron or more than 100 microns. Using nozzles are being used, but when we do that, actually we end up using we end up losing the resolution, because the nozzle is the structure through which the material comes out. So typically the filament that comes out of the nozzle have similar dimension to the nozzle. Suppose if you are using 100 micrometer nozzle, then the filament that comes out through the nozzle, that also will have around 100 micrometer size diameter of the filament. So that's what, so the extrusion bioprinting has lowest resolution, because due to this thing, because we cannot use a nozzle very narrow that is close to the dimension of the cells. So we have to use a nozzle, but when you use it higher dimension nozzle, then the resolution of the structure will be not very great. Another thing is that there are concerns with this cell viability, because of this extrusion process, because it's a pressure based application system. When pressure is being applied and it's causing generating shear stress, so that can cause damage to the cells. So but if you can optimize the process parameters, then the cell viability can be very good. But anyway, people have reported, or the researchers have reported, the cell viability starting from 40 to 95% cell viability, depending upon the process parameters, and also depending upon the hydrogel, on the viscosity of the hydrogel. That is thing. Another thing, because this is a nozzle based system, so nozzle clogging can be a problem. So that's why this has to be taken care of during the process. Nozzle clogging is nothing but when the nozzle is clogged due to the material, suppose the material or something, or if you have some particles within your hydrogel system, that can clog the nozzle. So nozzle clogging is an important is a challenge for this extrusion based bioprinting strategy. So you need to take care of things. Other than this, shear, as I mentioned, shear thinning materials, shear thinning hydrogel or shear thinning materials are very good for this extrusion based bioprinting. So we need to use shear thinning material for this extrusion based bioprinting. If some material doesn't have this shear thinning property, then we need to apply a lot of pressure to extrude the material. So that can compromise the cell viability. So all these are limitations with thing. But one important thing is, before actually using this extrusion based bioprinter, we need to optimize the bioprinter, and we need to optimize all the process parameters, so that we can come up with a very good printed structures, where we are not compromising the resolution of the printed dimensions, or we are not compromising the printing fidelity, and also we are not compromising the cell viability. So we have to strike a balance between these things in case of extrusion bioprinting. So when we discuss about bioink development, there we'll discuss in detail how actually we can control or modulate the hydrogel properties to print a better structures and also to take care of the cell viability. So thank you all of you for listening to this lecture. We'll see you again on the next lecture. Thank you very much.